create an organization global to create bridges for young people that I didn't have to work on.
Believing in humanity, but with action, and saying we must hold ourselves accountable and we must do better. We must do better.
Comment regarde-t-on le monde aujourd'hui et qu'est-ce qu'on veut qu'il devienne? Comment est-ce qu'on l'imagine?
Alors, bonjour et bon matin. J'espère que vous allez bien en ce beau mercredi. Nous sommes au Centre NAD UQAC, ici à Montréal, pour la 6e édition de MTL Connect. Comment allez-vous, Montréal? Très bien. On veut plus de café. En tout cas, ça nous fait plaisir de vous voir en si grand nombre, surtout ce matin. On rentre dans des sujets qui sont évidemment d'actualité. On va parler d'intelligence artificielle toute la matinée ici dans l'amphithéâtre et tout au long de la journée à travers des ateliers, des panels, des tables rondes, etc. Je vous rappelle, pour ceux et celles qui n'étaient pas là lors de la première rencontre de ce matin, le panel, je vous invite tous et toutes à aller explorer le 8e étage. Vous prenez l'ascenseur ici à l'étage, vous montez au 8e. Il y a un beau parcours expérientiel de différents partenaires qu'on vous invite également à découvrir. Et j'aimerais aussi souligner aujourd'hui qu'on parle de 2 thématiques, évidemment de culture et créativité, et on aura beaucoup de beaux sujets justement là, sur la découvrabilité des contenus culturels francophones dans la 4e édition des Rendez-vous France-Québec, un peu plus tard cet après-midi, mais c'est déjà parti, il y a aussi d'autres panels. Fait que ça se chevauche, intelligence artificielle, culture et créativité, bref, on a des super beaux sujets pour vous. Là, je vais juste faire un petit test parce que là, on va être captif, on va être dans un moment d'écoute et we're going to be absorbing content. Mais là, je veux m'assurer que la salle, elle est ici, qu'elle est présente. Montréal, est-ce qu'on est là? Oh, OK, j'aime ça. On est engagé, un public engagé, j'aime ça. Et les chers internautes qui nous suivent des 4 coins de la planète, merci d'être ici également. Alors, sans plus tarder, j'ai bien hâte de vous présenter notre keynote, notre grande conférence d'ouverture pour l'intelligence artificielle ce matin. Alors, elle est professeure chercheuse à l'Université de Nottingham. La semaine prochaine, elle va recevoir le Rising Talent Award, une palme décernée par Women's Forum pour ses accomplissements scientifiques. She's a PhD in computational musicology et aujourd'hui, elle va nous parler du sujet du Generative AI at the crossroads of art and virtual reality. Sans plus tarder, Montréal, accueillons Dr. Anna Shvets.
Déjà pour dire, je parlais très bien français, donc si vous voudriez me poser les questions en français, pas de problème. Je t'ai juste demandé de délivrer cette conférence en anglais pour internationaliser un petit peu les contenus, mais voilà. So, yeah, we switch to English language now. And as I was already presented, so assistant professor interactive music technology. I make part of the group special interest group that called Interactive and Intelligent Music Technologies within the Mixed Reality Lab at the University of Nottingham. And as the group name suggests, we explore new interactive ways of music expression in the virtual and mixed realities, focusing on co-creation with robots and artificial intelligence. So the current landscape of generative models illustrate a remarkable diversity across various media, reflecting cutting-edge advancements of artificial intelligence. Well, these generative models offer an impressive range of application, from the creation of the realistic images, music, voices, to the synthesizing of very complex content and cloning. All this is showcasing the dynamism and rapid evolution of the generative AI domain. in order to understand what we might expect from these models and what are their limitations, and also to operate the similar vocabulary, we'll do a quick overview of the technologies behind those generative advancements. So, first of all, what is artificial intelligence and how does it learn? Artificial intelligence is an algorithm that remembers learned patterns. So the learning scheme is quite simple. Given an input X, the model predicts its Y, and if the output Y is not what was expected, the error is calculated and fed back to the network through the process called backpropagation. And it's done multiple times, so this is error and trial learning that we heard about yesterday from another keynote presenter. So in that way, the model can get better. Before the network can process any input, all modalities, images, audio, text, are first vectorized. For an image, for example, vectorization involves representing the intensity of each pixel on a scale from 0 to 225. And then we normalize those values, so our final matrices will contain only 0 and 1s, the values between 0 and 1. And given the sequential nature of the text, we cannot apply the same methodology as for the images. Instead, we extract features for each word and determine its position within the sentence. Similarly, we process the time series data, including audio, by first segmenting it and then describing each segment using the extracted properties, automatically, of course. In this way, we obtain embeddings or vectorized representation of data. Okay, so the heart of training lies in the weight matrices. These are the values we adjust using the backpropagation, so through the error calculation process. Yes, and initially the weight matrices are initialized with random values, which are then multiplied by the vectorized data matrices of the input that we gave as embeddings. The result of this multiplication produces the hidden weighted matrices, which constitute the hidden layer. This illustration shows only one hidden layer, but in reality, there can be dozens of layers in neural network architecture. The weight matrices present the connections between these layers, and including the output layer. And the training process of these, well, it's mainly the adjustment of these weight matrices and the trained model. Actually, it's the weight matrices that we received after that for the inference. Okay. So a dense representation of data obtained through training is also referred as to a latent representation. So it captures the essential features of underlying aspects of data by transforming the input data into a form often of a reduced dimensionality compared to the original input. This transformation is carried out to preserve as much relevant information as possible while eliminating all the redundancies or non-essential information. Latent representations facilitate the understanding and manipulation of fundamental aspects of data, such as style, content, or specific attributes. These are used in generative network models to produce new samples. If we visualize the state of individual neurons at different stages of learning, we will see that earlier hidden layers have a very basic and fragmentary knowledge of input data, while neurons at later stage have more condensed knowledge. So in the beginning we have the layer 3A, then 4C, then 5A, and the units are the individual neurons and how they perceive the data from that input that we gave. Okay. We can also visualize the patterns the model has learned at different stages across the data ensemble through activation atlases. So these can show bizarre images representing condensed knowledge about specific groups and reveal how close some groups are in the model strengths understanding. But they are also used to, kind of understand where the margin of error can be. So, for example, because we are representing the data in the latent space using the common attributes, for example, for the artificial neural network model in its internal representation, the shapes of a shark, shapes, color, the size of a shark can be comparable to the to the flight, and in its classification, for example, or in generation, it might produce shark-like planes or planes like So just to say that what is evident for us is not evident for neural network, and the way it's trained, it does not possess the same classification patterns that we have. But we can exploit it later. We can see how the digital artist can exploit that as well. Okay. So let's examine some generative neural network architectures which belong to two different groups, recurrent and non-recurrent neural networks. Non-recurrent neural networks, such as variational autoencoder and generative adversarial network, GANs, are suited for processing non-sequential data, such as image generation. Meanwhile, recurrent network, including RNNs and transformers, can handle sequential data such as audio, video, or text. The variation autoencoder is structured into two main parts. The encoder transforms the input data in the latent representation, often of reduced dimensionality, capturing the essential aspects of data, and then this representation is used by the decoder to reconstruct the input data. The goal is to learn the dense representation of data that allows the generation of new instances similar to the original data. The GAN is composed of two distinct models, the generator and discriminator. The generator attempts to produce data, for example, images, that are indistinguishable from real data, while the discriminator tries to distinguish whether the input is real or fake. So it has the access to the what's called, to real data, what's called ground truth in learning, and it tries to understand what is real, what's fake, and then it feeds back the error margin, and thus both networks are learning. In the RNN, so recurrent neural network, each neuron receives not only the current state of the input, but also some form of the output from the neuron at the previous step. So this previous output serves as the network's memory, helping a model to make decisions based on the previously processed information. However, this type of network tends to forget the information present at the beginning of the sentence, sequence, basically, especially if the sequence is too long. To overcome this issue, transformer architecture was introduced that uses an attention mechanism that allows models to weight the relative importance of different parts of the input data, processing them simultaneously at once. This capability allows transformer to efficiently handle this type of data, sequential ones, like text or time series, by focusing on the most relevant elements of the task at hand. This approach significantly improves the quality of data generation and understanding. Another advancement is the multimodal generative models. So, generative model architectures present a crucial advancement in the field of artificial intelligence, offering the ability to process and generate data across different modalities, such as text, image, sound. Today, almost every model is actually multimodal. This ability to generate multimodal content relies on projecting these various modalities into the same latent space. Initially, this representation was primarily used for classification tasks. Two exemplary classic methods are perceiver and clip. Perceiver is designed to process all data modalities within the same architecture, while Clip uses two separate models, the language and image, to produce the latent representation and then put it in some kind of common latent representation and compute the similarity between those text and image pairs based on the similarity scores. The latest generative multimodal models such as Stable Diffusion or DAL-E both use the OpenAI's Clip models for embedding text-image pairs. Okay. The latest advancements in multimodal generation rely on diffusion models. Their name is inspired by the physical process of the one substance diffusing into another. Metaphorically, the network learns to distinguish these substances by predicting the content of one and then subtracting it from another. For example, in image processing, a noisy image is provided as an input, and the network attempts to predict this noise in order to subtract it from the image and retrieve the initial image. And in this in this process, actually, it learns the features of the image itself. The image processing architecture relies on blocks of convolution layers that first reduced the data dimensionality to a latent representation, then perform upscaling to recover the original resolution of the input image. It is possible to insert contextual information between these convolution blocks of upscaling and then use this information to condition the duration of diffusion model, thus trains. So models like Stable Diffusion are trained in this manner. For example, if the network is provided with the visual representation along with the textual description of an avocado and an armchair, at the end of the train, during inference, one can ask this model to generate an image of an armchair that looks like avocado and will have the interpolation of both embeddings in a visual representation. Okay, another recent method of generation pertains to 3D generation and is named neural readiness field, or NeRF for short. Neural readiness field is a method that achieves state-of-the-art results in synthesizing new views of a scene by modeling the volumetric scene function through the neural network. So this network input is a unique 5D continuous coordinates. So basically, 5 coordinates, it's the location, x, y, z, and then also the theta and phi, so the direction of Uven and the angle of Uven. And its output, the volume density, sigma, and the emitted RGB radiance, which depend on the view that spatial position. So basically the points and its color, right? Initially, not all coordinates are provided to the network. It starts with the spatial location, so x, y, z, and then just before the last layer, the direction and viewing angle are injected to model the volume density. To understand it more intuitively, let's take a look at this scheme. The model receives an object from different viewing angles. Then it generates the object's volume density, applying colors at the end. To generate a new instance from that trained model, we give the front and back images of an object, and thus we reconstruct a 3D representation from this trained model. Okay, so diffusion models and NeRF also enable the creation of animated 3D objects from textual description, thereby producing moving objects. So two recent methods, Align Your Gaussian that you see on the screen and Dream4D, allow to create personalized 4D content or effectively merge the movement sequences as well as merge the generated animated object into one scene in a current method, for example. In the first step of this method, the MV-Dream model is used to generate multiple views of an object from a textual description. So what we've done for NeRF, so we've been showing different the images of the object from different angles, where here we apply the model to generate those different different angles of view. Then, a text-to-video model is used to extract the desired motion modes. Both elements, the previously generated static 3D mesh and motion modes, are then fed to the video diffusion model that produces the dynamic 4D asset in motion. Text-to-image generation with the diffusion model is also applied to stabilize the visual rendering, kind of, because we still can see that it's kind of a floating, so the physics are not very well preserved. Thus, not one but 4 models are procedurally used to generate a dynamic 4D asset in motion from a textual description. The Dream in 4D method improves upon the previous process by incorporating NeRF, so that method that we learned just before, for creating static 3D objects, which allow for the static mesh and motion disentanglement. Disentanglement means separation, which results in more consistent rendering and more realistic animations. Okay, now let's see what is the state of the art of the generative AI in the VR. So first of all, let's sketch our world with the InstaVerse, an AI-powered 3D asset generated and visualizer that creates explorable words directly for the text input or a sketch. AI-generated texture, depth math, and the 3D meshes are available for download after this process of generation. The HDRI files, so 360 images, can be also imported as skyboxes to the Unreal Engine. They are also available for the download after the generation. The creators do not reveal the technology behind, but from what we've learned already, we can suppose that it uses the text-to-image generation with the NeRF applied afterwards. Okay, so now that we have our world, let's put some avatars with the PanoHead model, which is a new gun with a state-of-the-art performance in generating 3D textures models from a single images. This is the first 3D-aware generative model that enables high-quality, view-consistent image synthesis of full heads in 360 representation. Now, after generating our world and having placed some 3D avatars, let's make them talk. So it's a big revolution, actually, that happens right now in rendering non-playable characters NPC. I think you all heard about that. Rendering them interactive is actually based on this technology. So Audio2Face model is based on a deep bidirectional LSTM network. LSTM, it's a type of a RNN network that we saw before. And the attention mechanism from Transformer is applied to discover the latent representation of time-varying contextual information within the speech and recognize the significance of the different information contributed to central face status, basically the face expression. NVIDIA Omniverse 3D Animation 3D tool cloud API uses Audio2Face generative AI to bring to life characters in Unreal Engine and other rendering tools by creating realistic facial animation from just audio files. So you're provided just an audio files of yourself or your character, and that produces the animation with all the facial recognition and the alignment with the facial movements. NVIDIA Omniverse is an open platform compatible with the MetaHuman framework of Unreal Engine and is currently supporting a motion to audio feature. So let's see it in motion. So we can adjust, we can do interpolation between two emotions. That will also affect the audio we import.
Where is it? I can't see it. I can't see anything. But I know it's there. Waiting.
The beige hue on the waters of the loch impressed all, including the French queen, before she heard that symphony again, just as young Arthur won.
Okay, I have a few jokes here. What do you call a fish without any eyes?
Okay. So, want to make your users see their bodies? Well, totally feasible with AvatarPoser, which is the first learning-based method that predicts full body poses in world coordinates using only motion input from the user headset and hands, so the triggers. The method builds on a transformer encoder to extract deep features from the input signals and decouples global motion and learned local joint orientation to guide pose estimation. So while training we give both, and then while inference we give just hands, and it predicts the pose of the body. Okay, so finally, you can also use the Master X Studio that allows the generation and correction of generated 3D meshes, UV map, texture, rig, skin, and animation inside Unreal Engine editor. So as we saw, these tools are very business-oriented, so which facilitates and speeds up actually the prototyping. Well, however, artistic usages of these are quite limited. In a moment, we will see how digital artists practically use the generative AI and explore how they do that. So basically, yeah, this is how they have already the templates ready for you to use, but yes, you can adjust them to your needs in the editor. Okay, so tendencies. Due to the AI ability to place similar data examples into a close proximity in a latent space, as we saw, it can offer unexpected connection that might inspire new ideas. For example, the Kepler's old drawing being associated with the Earth images, kind of decoupled Earth images, generated by DALL-E model, result in a whole new representation created by the UK digital artist in a virtual reality space. So she was inspired by generation that DALL-E made and that brought her creativity to a whole new level. Or, because of the close distribution of similar data in the latent space, it can be used in a metamorphic visual compositions, very in the theme of the conference itself, metamorphic, with a slow transition from one data point to another in a seamless manner, and shows the artwork of the French digital artist. It's interesting that the imperfections of the current technology can be used artistically. So we see that there is a problem with the stability sometimes, or AI is not able to generate long, consistent in-views video, or it can have some problems with the physicality of the objects generated. But that's not a problem at all. We can change the discourse and, for example, adapt it and actually use those as the creative means. So this is an interesting example of how technological limitations shape human inspiration. So we can actually make the focus on these in-between moments and not on the general narrative that we accustomed to. Okay. Because each neuron has condensed knowledge at different stages of training, this can be creatively used to produce a dreamy world-like feeling. In this work, UK-based digital artist submerges the user into a peaceful and immersive journey through the imagining of the neural network, as he tells himself. The series nature portals explore the implication of a world where nature and technology have become so intervened that it questions the fundamental difference between the artificial and natural. Yeah, quite beautiful, actually. I suppose that he used some biological model to that, because we clearly can see these bio roots of some microorganism in that. Okay. Yes, so the latent space exploration may be used not only for video generation, but allows its integration into multi-sensory AI artwork created by the US-based artist, The work by this artist shows the shifting paradigms of creativity itself. Instead of generating the visual material, which he did not generate at all, it's AI that generated it in real time. The artist focuses on the idea implementation through AI-generated content and the multi-sensory ways of exploration. So instead of generating content, he focuses on the idea and how user can explore them, right? In his earlier work that shows that was shown this year at the NVIDIA Global Technical Conference, he's using the video generators and maps the colors and modes of movements to the moving ocean of particles, and it's done real time actually. The artist had a console where he was choosing the class to be generated real time, and of course it required a powerful computer device and substantial energy consumption. So this leads us to the last part of the presentation, which is the main question to be answered. Can we make a sustainable art with generative AI? Okay, so the problematics of conventional computing consist of a physical separation between memory and processing unit, which is a source of a power waste on shuttling data between those units. And as we saw, the AI model are heavily relying on this shuttling of data. So computing the weights, saving them, retrieving them, computing, saving, etc. So another problem in the conventional computing is the clock signal, which is not optimized for complex cognitive tasks, which is not the case of our brain, for example, which manages the task asynchronously at the same time, fully parallel. Prominent solutions to these problems are in-memory computing and event-based system. The event-based system and in-memory computing, together with the massive parallelism, are the three fundamental principles which have led to the development of the neuromorphic computing and to the realization of highly efficient neuromorphic platforms. There have been experiments that already confirmed the efficiency of those types of computing. So, for example, this experiment with the Loihi chips shows that neuromorphic platforms demonstrated 100 times lower power consumption, running a real-time deep learning network, benchmark compared to the GPU, and 5 times lower consumption compared to a specialized IoT inference hardware, which is already optimized for low-power devices. After scaling the network up by 50 times, this platform maintained real-time performance and used only 30% more power, whereas IoT hardware used 500% more power and was no longer real-time. Okay. So the efficiency of these computing chips relies on input from neuromorphic sensors, which imitate the way we perceive the information, our biological way of perceiving information. Contrary to common belief, our eyes do not receive the entire image simultaneously. We first see the brightest pixels, then the darker ones, and then our brain is calculating the whole image real time, all the time. So it's very powerful computing device, our brain. In fact, this principle applies similarly to audio or olfactory systems. To simulate this sensory input, if we don't have the access for them, for example, we must use the we must convert the image to the time-distributed data information, which is needed for spiking neural networks to be processed. And this type of neural networks is particularly efficient with those neuromorphic computing platforms. So in spiking neural network, neurons spike asynchronously only to communicate information to each other. Spiking neural networks have garnered significant attention in scientific literature due to their low memory and energy consumption. The reduction in energy consumption during the training of this network is linked to the decrease of an amount of data needed to train a performant model compared to a conventional neural network. And we'll see that it's actually true. This makes the training and usage of those models based on spiking network more environmentally responsible, and applicable to low-power devices, including VR headsets. I mean, the Quest types, not the very expensive one that Apple can produce. But yeah, the mathematical formalization uses the model of a current. If a membrane potential reaches its threshold, the spike is emitted and transmitted to the next neuron. It's quite like our brain, actually. Thus, the output of a spiky neuron will give two matrices. The matrices with the continuous values and that show this activation potential, and till they reach the threshold, and the zeros and one matrix, so fired neurons. And during the inference, only the second matrix will be used. So only the 0 and 1 matrix will be used, which is very energy efficient, actually. The patents by Apple for VR headsets suggest that the use of integrated DVC cameras, so dynamic vision cameras with this sparse vision, which will work with the spiking networks, obviously, to trace sparse distributed data from these neuromorphic sensor devices. With this technological premise, a fast energy, fast efficient neuromorphic AI, how can we apply it to the domain of art? Okay, so the first most natural question to that was how we can actually use that in the generative AI, right? So the spiking network were primarily used to the classification tasks, so where the artists, where the scientists were trying to actually find some algorithm that would be efficient. So in the generative domain, there were very few examples, and nobody actually treated it as sequential data. So the experiment I've done 2 years ago actually focused on those type of questions. So is it suitable for image generation and, for example, music information that is embedded as an image generation, image information? Then whether it's good for the sequence memorization, whether it's better for than the conventional classical type of neural network. How does it react to data scarcity and sparsity? So sparsity, because in spiking network can have sparse data, and this sparse data is actually energy efficient. So how can we treat them? And data scarcity is they are really able to be trained on a very little amount of data. So these were the questions that I asked myself during this experiment, and I used basically two data sets. The one that was already existing, so movie mist, and was some verification, so the sequence of images of handwritten digits, and the data set that produced myself. So I basically used the formalism to embed the chord information. So each frame is actually a chord in a chord sequence. So the task of the network was to produce this last frame, given the four input, 4 instances of the input sequence, right? 4 elements of the input sequence. And the experiment actually showed that with the modest data set, I used the biggest data set I had. It was 2,000 data points, which is really nothing, because actually to train the conventional neural network, we need millions examples of data. So we can fine-tune the model, adjust the weights with the tens of thousands of data points. So basically, it's like 10 times less than the fine-tuning data set, not even the training one. And we see that the conventional classical and conval STM just not capable to process this. So in the first row, we see the ground truth that should have been predicted, and the lowest row gives the prediction, and we see that it's just noise that classical LSTM produces, whereas the spiking conval STM was able to kind of capture this information, the spatial distribution, the position, all those does in very, very sparse kind of situations. So yeah, that was a success. So now that we've proven that neuromorphic computing can be efficient, and the duration with the number of components can be efficient, how we can apply that to the VR, and especially for building interactive music applications, right? So the main angle of view. Well, while the idea of creating eco-responsible music VR application has its value on its own, I wanted to solve some concrete problems with this approach, which is transforming a 2D digital artwork, audiovisual one, to an interactive VR experience. So, amid the so this is the visualization of music extract, basically, what it represents. And the question how we can actually translate that to the virtual reality. And here we have a lot of problems. So even if we apply generative AI to, you know, like kind of generate the objects, they are actually appearing, disappearing. How do we do that? I mean, we can't do that with AI, really. I mean, in order to model it like manually, it's too much of time, and really we need to find it another way. So, and another question, it's a 2D artwork, right? How do we place it in the VR world so that takes all the place, not just, you know, some screen in the VR world is not interesting, right? So to overcome this problem, the time-distributed data generator from these neuromorphic paradigms was applied to produce a time-step matrices for each frame of the video. This basically involved splitting the image, first of all, cutting off the background, then splitting each image into RGB matrices, and each of these RGB matrices was passed through this time-distributed data generator that generated the spikes, right? So in the beginning, it was transforming the intensity of the color to the time. So the most intense, the earlier it comes to in this raster plot, and so on. And while we needed only 2 interactive walls in the VR music application, I also then after that generation I applied the spans. So the 2 spans that were kind of then captured then all together, right? Like time distributed data. We take the most intense one, and we are putting them together into different matrices, and we place that in the VR space. And thus, all the non-important information is cut out. So we have kind of a specified data, and it's actually very good for the VR environment. So in order to measure the how performant it is, I use the internal tool in Unreal Engine that allows to capture the FTF, the time. Sorry, I'm a little lost. FPS, sorry, frames per second. So frames. Basically, we need to have, in order to have the performant VR application, we don't need to have these drops below a certain threshold. And in the data that were treated that in neuromorphic way, we had only 2 spikes below 10 FPS. And this drop, just to say that this application was not optimized at all. It was a prototype research one, so no optimization technique was applied really. And when I tried to put the backgroundless frames just to produce kind of a similar representation, I saw that actually it has 3 times more drops below 10 FPS, and like 30 drops below 30 FPS. So basically, the experience is was just lagging, right? And when I tried to apply the standard non-treated images as is, well, I saw that, well, basically it was dead. I mean, there are too many drops below the 10 FPS, and basically my computer just freezed. I mean, you can just even imagine to put that into the low power, low memory VR headset. So yeah, that was it. Also, as a point, the size of the disk size for the images. So for the processed images and backgroundless images, they took 2/3 of the space that original frame occupied. So yeah, basically, I think it's quite efficient. So let's see the final result of this. So yeah, I also, to make it more interactive, I placed the interactive object that can be manipulated by the user, and those projections of the image, the projections of the image were made as the interactive walls that the user could traverse and receive the additional audio feedback. So the audio feedback that was like kind of enhancing the audio space of the application. So just in a moment we will traverse the walls, so you'll hear for yourself. And that was done with the meta sound feature with the inside Unreal Engine. And just to say that those particles are reacting to the feature of the sound, so to the velocity of the sound wave. So yeah, that was basically my experience with the introducing the neuromorphic computing to the VR domain to build an interactive music application. And yeah, that's it. Thank you for your attention. And as I said, you can ask questions in French. I can answer you in French if you are more familiar with that language. Yeah.
Thank you so much, Dr. Shvets. Thank you, Anna. Merci beaucoup pour cette excellente présentation. En tout cas, I think we seeing all of that work and the opportunities that are endless, pretty much, and you really went in the crux of the subject and dug deeper. So again, on behalf of all of us here, thank you so much, Dr. Shvets. As Dr. Shvets mentioned, we do have time for questions. On a le temps des questions, soit en français ou en anglais. Est-ce que vous avez des questions, cher public? Si oui, on a juste à lever la main. Et on va vous passer un micro et juste vous présenter en français ou en anglais et votre question. Merci.
Thank you for your presentation. I was wondering, from your experience, how far or how close are we from to our augmented reality generative experience?
Yeah, well, basically, I was not doing the augmented reality, really. So it's the domain specialization of my colleagues. So I was more focusing on this VR representation. But basically, the same principle you can apply actually to the augmented as well. I mean, the augmented reality also uses the low power and low memory devices, right? So the same principle of sparsification of this data that we can use while maintaining this important information. It can be used as well to kind of, to augment the performance with those systems as well. As I say, I did not test it myself, but that just should work with them as well, because it's the same principle. So whenever you receive the sparsified input, this will be better treated by your low power devices, right? So these neuromorphic principles, they can be applied to different domains and really to any low power device paradigm that you might expect.
Thank you.
Thank you for your question. Est-ce qu'il y a d'autres questions du public? Oui, il y a une question au fond. Votre nom et votre question.
Excuse-moi. Hi, my name's Sam. And my question was, do you ever see kind of a future for some of your research to be turned into a Unreal Engine SDK add-on or anything like that to make it more publicly accessible?
Yeah, totally. Thank you for this question. Actually, yes. I'm right now applying for the grant that kind of tries to do that for the musicians. So because we saw the potential, right? We can do eco art. Well, we can stay creative and not using these wasteful, that waste of energy and memory. So yeah, I mean, actually, I was thinking about create some kind of pipeline that, some kind of optimized pipeline for the musicians. So then they input their audio data, and then this specified information with images generated by AI, but with this neuromorphic paradigm, comes out, and they can choose whether they like this generation or don't like this generation. So basically, construct some pipeline that would allow artists to use this type of technology for their concert, live performances, and so on. So basically, yeah, thank you very much. It's exactly what I'm trying to accomplish.
Yeah. Great question, spot on. We have time for one or two more questions. I know I was very curious myself about neuromorphic computing. I think it's a subject that's quite new to us, seeing pretty much how us humans and our biology works adapted to how then AI can input the data. Can you maybe tell us a little more about neuromorphic computing in general?
Yes. Well, neuromorphic computing today is really quite developed field already. We have the startups, we have the university, we have big companies that are already producing those neuromorphic chips. For example, Loihi example. So Loihi chip, which is a very small one, uses this distributed data input extremely low power and performant and quick. And we also have the Spinnaker. Spinnaker, it's a Manchester-based supercomputer that's based on the RAGs of those computational. So basically, this parallelism, massive parallelism, is embedded into the hardware of that machine. And you can even have, as a researcher, have the possibility to use those kind of power to do your research. So these facilities are already there. There are also the other smaller startups that are also trying to kind of come to this technology, because it's very promising in autonomous systems, right? So like car driving or robotics, or for example, the type of situation when you really need edge computing implemented, where you don't have the access to the network, satellite or whatever, under the ground, under the water, where you need this autonomous system running on very little of power, right? And yeah, I mean, those these initiatives are not yet the current stream, because yeah, we have NVIDIA that basically took everything, right? Yeah, yeah. But we also see these problems, the environmental problems that we've been talking already yesterday, and what that brings with these data centers, etc. So I know that there is even the former COE of OpenAI that went into actually who left actually the company and went into exploring these decentralized systems. So just to say that there is real potential in those, and with those environmental problematics that we have today, we will be just obliged actually to turn into those low power paradigm computing devices. And yeah, this neuromorphic computing is the answer to our problems of today, environmental issues with the AI.
Very, very, very interesting. I want to say I'm learning a lot about neuromorphic computing, so this is fascinating for me personally. I hope you have all been enjoying this, both at home and in this auditorium today. I have room for one more question. If anyone else, une autre question du public, si quelqu'un aurait une dernière question pour Dr. Shvets, oui? Why not? Merci beaucoup. Votre nom et votre question.
Bonjour, merci beaucoup pour la présentation. Mon nom, c'est Arthur. J'ai une question plus concernant l'art, la culture de demain. Pensez-vous que l'IA générative est la nouvelle forme d'art qu'on retrouvera demain? Et si oui, est-ce que c'est une menace pour les actuels arts numériques ou pas que nous avons en ce moment?
Une excellente question, de nouveau, merci beaucoup de l'avoir posée. Bah, justement, avec, moi je crois que non. C'est-à-dire que je crois que l'IA, c'est juste un outil qui donne d'autres possibilités. Mais par contre, effectivement, ça change notre paradigme de créativité. C'est-à-dire qu'au lieu, effectivement, de générer le contenu, donc au lieu d'un peintre qui faisait ses toiles pour après, ou un animateur qui faisait plusieurs images pour faire une animation, bah, là, on utilise l'IA générative pour faire ça pour nous. Par contre, nous, en tant que les humains, nous avons la capacité justement de se concentrer sur autre chose, en fait. Donc, sur l'idée même. Donc, comment on peut améliorer notre narratif, comment on peut améliorer l'expérience de notre utilisateur. Parce qu'en fait, il y a un autre point, c'est l'interaction. Donc aujourd'hui, l'utilisateur, il attend cette interactivité. Justement, c'est une des applications que je justement développée. Et je faisais des expériences, les expérimentations avec les gens lors des festivals en France. Et justement, tous les gens ont adoré interactivité. Par contre, ils ont dit que c'est pas, je demandais, est-ce que cette musique représentée dans une telle forme, la musique représentée lors d'un concert standard, est-ce que ça sera mieux, pire, ils ont dit, ça sera différent. Et ça, c'est une catégorie qui eux-mêmes ont rajouté. J'ai pas rajouté cette catégorie, j'en ai pas pensé. Eux-mêmes ont rajouté plusieurs, en fait. En fait, c'est une forme alternative des représentations. C'est pas le remplacement. C'est juste une addition pour les gens qui ont plus la technologie, qui attendent en fait cette interactivité, cet art, de l'art des futurs. Et justement, l'IA nous permettra en fait de faire ce parcours beaucoup plus personnalisé qu'on ne peut pas imaginer aujourd'hui. C'est juste par rapport au temps, par rapport à la production de contenu, si vous voulez. Et si avec l'IA, on pourra générer le contenu optimisé pour notre utilisateur, en prenant les caractéristiques de notre utilisateur, justement, c'est juste un outil. Donc, moi, je ne crois pas qu'on sera remplacé, juste on devra effectivement adopter ces nouvelles formes de pensée.
Oui, et très bonne question. Moi, j'ai quelqu'un qui m'a dit, c'est pas une question de est-ce que l'IA va faire partie de notre quotidien dans notre domaine. En gros, c'est quand, et c'est déjà le cas. Il faut l'incorporer dès maintenant dans tous les secteurs d'activité. Dr. Shvets, merci beaucoup. On applaudit Dr. Anna Shvets. Thank you very much. Alors, nous allons prendre une petite pause d'une dizaine de minutes. Je vous invite à quitter par la porte d'en arrière. Si vous voulez retourner pour le prochain panel, on va retourner par la porte ici en avant. 5-10 minutes, on se retrouve pour le prochain panel. Je vous remercie. À tout de suite. Merci.